According to the dictionary, equilibrium is a state in which opposing forces or actions are in balance, so that one is not stronger or greater than the other. That definition can also be applied in everyday chemistry. At this plant in South Arkansas, where about half of the world's bromine is produced, examples of equilibrium in chemistry are everywhere you look. In that orange pipe behind me is a brine, rich in bromide, and it's at equilibrium. It's been sitting for millions of years, about 1.5 miles below us, until it was pumped up just a few minutes ago. The concentrations of the various chemical species in it haven't changed in those millions of years. The good folks at Great Lakes Solutions are about to inject elemental chlorine, Cl2, using that stainless steel pipe. And in the few seconds it takes it to mix together and travel from here to up here, a new equilibrium is established. Welcome to Chemistry at Work. Today we're visiting Great Lakes Solutions in El Dorado, Arkansas, because it's the perfect place to show the chemical concept of equilibrium, where chemical equilibria are changed in order to produce elemental bromine. Bromine is used in hundreds of products, from water purification and agriculture to pharmaceuticals and flame retardants. This plant will help us demonstrate what equilibrium is and how it works. The problem is, at the plant itself, everything is sealed up. You can't actually see changes in equilibrium happening. So we went into one of the on-site labs. First, so we could see how bromine is made, and second, so we can show how chemical reactions reach equilibrium as things change. There we met Tommy, one of the great lab technicians at Great Lakes Solutions. So what do we got here that you're going to show us?
Okay, what we got set up is a 5-liter round bottom flask with feed brine in it containing sodium chloride and sodium bromide.
Okay.
That we'll be releasing the free bromine from.
And over here, my first hint that this was chlorine was that label?
That is correct. We have about a 2-pound chlorine lecture bottle that we'll be using.
Okay, so just like they do in the plant, except we're going to be able to see it here.
Mm-hmm. That is correct. Okay,
and there's a beaker there.
This is a beaker containing the actual feed brine we feed into our bromine towers.
Wow, that is noticeably heavier than regular old water. So there's a lot of sodium chloride in here.
That's correct.
And some bromide.
Yeah, at about 4,000 parts per million. We're going to add chlorine vapor through this needle valve and through this Teflon tubing, which is subsurface in the brine.
Chlorine and bromine aren't any fun to breathe. So before Tommy adds chlorine to make the bromine, he starts up the hood to keep us all safe. At first, Tommy just trickles the chlorine in. But even with tiny amounts of chlorine added, we begin to see a color change. In low concentrations in water, bromine is a beautiful yellow or amber color. By adding chlorine, Tommy has established a new equilibrium. An equilibrium where bromide is transformed into bromine and chlorine is turned into chloride. Let's think about what's happening in this reaction. We start out with a solution of sodium bromide and sodium chloride, and we know that elemental chlorine is used to convert bromide ions into elemental bromine. That's the chemical reaction, and it happens to be a reduction-oxidation reaction. And if you're interested, we have another video that discusses the reaction from that viewpoint. But here, we want to examine what a chemical equilibrium is. And for that, we don't necessarily need a reaction equation, but instead an equilibrium expression. Chemistry students learn that for a chemical reaction of this general form, we can write an equilibrium constant expression of this form. We multiply the concentrations of the products of the reaction and raise each concentration term to the power equal to the coefficient found in the chemical reaction. We divide that first expression by the product of the concentrations of the reactants, also each raised to the power of the coefficient in the chemical reaction. That expression is set equal to a constant, K sub EQ, the equilibrium constant. We don't have time to explain everything there is to know about equilibrium expressions, but the reaction we're exploring here, the conversion of bromide into bromine, helps us to understand qualitatively why equilibrium expressions work in this fashion. To figure that out, let's focus for a moment on the bromide ions. They've been sitting deep underground for millions of years. Plenty of time to come to chemical equilibrium. And then suddenly, elemental chlorine is added. In order for a chemical reaction to occur, the molecules reacting have to actually get together. They have to collide. One reason chemists do a lot of chemistry in solution or in the gas phase is that all the chemical species present are free to move around and collide. But even when a collision occurs, not every collision results in a reaction. If atoms are going to exchange or share electrons, the orbitals that contain those electrons have to line up correctly. But sooner or later, and mostly sooner, every molecule of Cl2 will bump into a bromide ion, with everything correctly oriented. A bromide slams into a Cl2, and presto, a chloride takes off with the electron from the bromine atom. But notice, we haven't yet made Br2, elemental bromine. Instead, we have a molecule with one bromine attached to one chlorine. It takes a second collision of this reaction intermediate with a second bromide to kick out the second chloride ion and to actually make Br2. When you think about the reaction requiring collisions to proceed, the form of the equilibrium expression makes perfect sense. Why do we use concentration terms? Because if concentrations are high for a species, the chances are much better that it will collide with its reaction partner to make the reaction proceed. Down in the denominator, where we show reactant concentrations, if the concentration of chlorine is high, the odds are just better it's going to collide with a bromide. And why do we square the bromide concentration? Because we have to have two separate collisions with a bromide for the reaction to proceed all the way from starting materials to products. Each collision has roughly equal odds, and overall, the odds of two collisions in a row occurring in a given time frame are lower than having just one collision occur. In this time lapse of the reaction, we see a practical demonstration of driving an equilibrium by adding more of a starting material. The color of the bromine product gets more and more obvious as Tommy adds more and more chlorine, a starting material. Most of that chlorine he adds is immediately consumed, but every time he adds chlorine, collisions with bromide can occur, and he sets up a new equilibrium that favors the production of more bromine. So far, we have only talked about the terms in the denominator. What about all that stuff on top in the numerator? Notice it's pretty similar in form, although not identical to the terms on the bottom. It is, of course, the concentrations of the products, not the reactants. Why do the concentrations of the products matter? One idea you may have learned about already is the idea that all chemical reactions are, at least in principle, reversible. Now, in this case, that reverse reaction is pretty straightforward. If a chloride collides in the correct fashion with a Br2, it can create the same bromine-chlorine intermediate that we saw in the Ford reaction. That intermediate can collide with a second chloride and make elemental chlorine, Cl2. Just like for the Ford reaction, the odds of these collisions are proportional to the concentrations of the species involved. High concentrations favor the collisions. And once again, we're squaring one concentration, the concentration of chloride, because for the reverse reaction to occur, two collisions with chloride have to occur. So we have a term that relates the concentrations of the reactants to the probability of the Ford reaction. And that's in a ratio to the term that relates the concentration of the products to the probability of the back reaction. That ratio determines where the equilibrium lies. But one look at this flask tells us that the Ford and reverse reactions aren't equally probable. There's a nice red color from the elemental bromine, but we don't see any real sign of the green of elemental chlorine. Why not? The reason for that lies in the only part of the equilibrium expression we haven't discussed, the equilibrium constant itself. Every chemical reaction has its own unique equilibrium constant. The product of multiplying and dividing the concentrations of the various species in the right-hand side of the equation must equal the equilibrium constant. The equilibrium constant is just that, constant. It only changes for a particular reaction if the temperature changes. If the equilibrium constant is big, that means the products are favored. If the equilibrium constant is a very small number, that means the numerator, the products, are small compared to the denominator, the reactants. So the obvious question is what makes an equilibrium constant big or small? That is determined by how stable the products are relative to the reactants. The more stable the products, the lower in free energy they are relative to the reactants, the more they're favored. It can be difficult to remember that different amounts of products and reactants are required to achieve an equilibrium. You might think we need equal amounts of products and reactants to be in equilibrium, but this is not usually the case because only rarely are the products and reactants equal in energy. This scale is kind of a metaphor for an equilibrium. Suppose I put one cylinder on one side of the scale and one block on the other side. The concentration, the amount of things are the same on each side, 1 and 1. But clearly, the system isn't in balance. Of course, the reason the scale is out of balance is because one of the blocks weighs more than one of the cylinders. Don't take this metaphor too literally. Think of the equilibrium constant as kind of a scale, but one that measures chemical reactivity rather than weight. I can balance out the greater reactivity of the blocks by piling more of the cylinders on the other side. For the reaction here, chlorine is more reactive, which is another way to say it's higher in free energy, or heavier in our metaphor. Bromine is more stable, or less reactive, both of which are other ways of saying it's lower in free energy, lower in weight in our scale metaphor. The high reactivity of chlorine blocks means that when the system is in equilibrium, when it is balanced, that many more bromine cylinders are present relative to chlorine blocks. Of course, we don't really use a scale, we use a mathematical expression, and the equilibrium constant tells us the relative amounts of products and reactants needed to achieve balance in the reaction. How do we determine the value of an equilibrium constant? Well, these days we may be able to calculate it from first principles, but usually we just set up a reaction and measure the concentrations of the different species at equilibrium in order to empirically determine it. In the case of the reaction of chlorine and bromide to make chloride and bromine, the equilibrium constant's approximately 1.3 times 10 to the 9th. 1.3 billion to 1 is the ratio of the products to the reactants. 1.3 billion? That means any set of concentrations that satisfy this equation will have to greatly favor high concentrations of elemental bromine relative to elemental chlorine. That makes sense. Chlorine's much more serious about getting its outer valence shell filled with electrons than bromine is. As chemists like to say, chlorine's much more electronegative than bromine. In terms of our collision model, that means it's just less likely for a chloride to give up its electron to a bromine than it is for a bromide to give up its electron to a chlorine. The second factor that favors the Ford reaction is that chloride has a stronger interaction with water than bromide does. Now, in our animations, we've deliberately excluded the water to keep things simple, but for chloride to collide with a bromine, we have to get the water that surrounds it out of the way. And that's just harder to do for chloride than it is for bromide in the Ford reaction. So when we add those energetic factors together, we get a reaction where the equilibrium expression strongly favors the formation of products. 1.3 billion! Let's consider once again the equilibrium expression. Whenever a reaction is at equilibrium, this expression must be true for whatever numbers we plug in for the concentrations. The equilibrium constant is a constant, but the concentrations, those can change. Now, in the moment that chlorine is added to the reaction's not at equilibrium. This equation probably isn't true. It isn't satisfied. But very quickly, the added chlorine reacts, diminishing the concentration of elemental chlorine and raising the concentration of elemental bromine until we come to a set of values that satisfy this equation, and a new equilibrium is established. As more chlorine is added, yet another equilibrium is established, with still more bromine being produced, until eventually most of the bromide is converted into bromine. Understanding equilibrium is critically important to chemists and their work. Today we've seen a great example of that in application. The brine that's processed through this plant enters in a state of equilibrium. Once it's brought into the plant, though, that equilibrium is disrupted as new chemical species are added. But they react, and the concentrations change, and at the end of the process, the resulting solution has once again returned to a state of equilibrium. Only now it is rich in bromine.